Hello everyone, welcome to Math 153, Statistical Reasoning. We have a poll. Do you feel vulnerable to identity theft? My dad says, yes, I could tell you the story. We asked 1,003 people and 588 said, yes, I want a 90% confidence level. What's the best point estimate? You know how to get a point estimate of a proportion you divide, right? We have 1,003 that we asked, and we have 588 who said yes. So I do 588 divided by 1003, and you're thinking, this is like chapter 4 basic probability stuff. Exactly right. They want to round to 3 decimal places, and it was 0.586, so I put in 0.586. You love me. What's the value of the margin of error E? So what we will use is StatCrunch. So let me show you this really quickly. There's no data in it. I have to put the data in. We go to Stat. We go to Proportion Stats. We do one sample. I don't have any data. All I have is the summary. I know the number of people. Yep. So stat, proportion, one sample, summary. And then it says, how many successes did you have? And I say 588. They say, how many observations were there? And I say 1,003. And what are you trying to get? Well, they asked me to get a 90% confidence level. So I want a confidence interval, and I want it 90%. There are several different methods. We will always use this same one. You don't have to do anything but that. There's your lower limit. There's your upper limit. This looks like something you want. It is not anything you want. In order to find E, and the examples in the book show this when you read it, they also do it in the videos, you need to subtract these and divide by 2, right? So 6118, 5606, you subtract and divide by 2. I'm selecting and copying. I'm pasting. I'm selecting, copying. I'm subtracting, I'm pasting. I'm equaling, I'm dividing by 2. There's E, 0.025, round at 0.026. Fantastic. What's the confidence interval? Well, I'm thinking it goes from 0.561 to 0.612. 0.561, 0.612. I'm rounding to what they say. There's 3 ways to say it wrong. There's one way to say it correctly. And I'll let you look at these because I don't want to take the time, but that's the answer. Read them carefully. That's how you do them. And there's a bunch of them. That's how it works. So I recommend that you open up StatCrunch from a separate window because you'll be using it all through this section. And a lot of times you will be entering the values yourself. So we have a StatCrunch window there, and we can tile our windows. Okay, so I have my homework opened, and I have a new fresh StatCrunch window, and I've tiled so that I can work with these things. And let's work some of these problems. Use the sample data and confidence level given to complete the parts. So they want a 95% confidence interval. This is a study of cell phone use and brain hemispheric dominance. I wonder what that means. I think it means whether you're left-brained or right-brained. Interesting stuff, isn't it? Yeah, speaking as a statistician, I have to tell you, probably 3/4, maybe more, of what you hear about Fred is left-brained and so he's good at art and things like that, they're nonsense. So just saying. Anyway, we have 2,532 people who got an email, and 901 of them responded. And we want to know what proportion responded. So we go to stat. We go to proportion stats. Everything from now on for a while is one sample. We'll have a later chapter that has 2 samples, but right now they're all one sample. We don't have the data. We don't know Fred returned it and George didn't, and so on and so on. We just have the summary values. And so we select this. The number of successes is 901. The number of observations is 2,532. We are doing a confidence interval, and they've told us to use a 95% confidence interval. I don't know if I want to say it a lot, but I get a little annoyed with them. And the reason I get a little annoyed is they change this value all the time. The reason they change it is to teach you that you could have different values. But what they do is they do it arbitrarily, right? This number, when you work this problem, will be different. And this number will be different. And they have a random number generator that randomizes, it makes up a number, so every single person's problem is different. If you finish it and say similar problem, it'll be the same problem, and these numbers will be slightly different. That includes this number. And let me tell you just once, this annoys me because there's a reason you have chosen the alpha you've chosen. So I recommend use alpha of 0.05. So you're getting a 95% confidence interval because that's what most people use. That's what makes the most sense. That's the established standard in the statistics community. Some subject areas like medicine, they require that. That's what you have to use. You have to use an alpha of 0.05. When MathLab randomly chooses, it makes it feel to me as though they don't care, and you should care. You should think about what it should be, and sometimes it should be 0.10, and sometimes it should be 0.01, but it depends on the problem. It's a thinking class, not a math class. And I get annoyed when they just change it willy-nilly as though it doesn't matter. No, it does matter. Why? Because you'll get different results. Anyway, we want to know the best point estimate. And one way to do that would be to use a calculator and divide 901 by 2532. And if you love using a calculator, you can do that. But if you've set this up in StatCrunch, when you compute, it will tell you the sample proportion, the sample prop. This is p hat right there. And so just enter it, round it to what they say, 3 decimal places, it's 0.356. Excellent. And then identify the value of the margin of error. In our textbook, they give you two formulas. One is to find the point estimate, and we don't need this formula because StatCrunch just gave it to us. The other formula calculates the margin of error, and that one is more useful because we don't have that. If you look at the StatCrunch window, it gives a lower limit and an upper limit. And here, this is this upper limit, and this is the lower limit. And so basically what you do is you subtract and divide by 2. And does this kind of make sense to you if you think about it? If you think about it, there's some middle value, right? It's not there, it's this 355. And they subtracted something and got this, or they added something and got this. If you would rather, then you could take this 355 and subtract the 337. That would give you your value of E, because we know take this, subtract, you get that. So usually for me, it's easiest to do the 3.7, the upper minus the sample proportion. In order to calculate E, the margin of error, I take the upper limit, which is 0.3744936, and I can select it, copy it with a Control C, paste it with a Control V, and subtract over in this window, subtract the sample proportion. P hat, I copy it with a Control C, I paste it with a Control V, and I get the equals. It's 0.019 once I have rounded things. Getting back to the exercises, I put in that 0.019, 3 decimal places. Construct the confidence interval. We've already done it. It goes from 337 to 374. 0.337, 0.374. And what does this mean? We're 95% confident that the interval does actually contain the true value. That's the right way to say it, and you want to practice that. I like this question a lot because it involves genetic experiments, and you can remember this is Gregor Mendel, who was a Polish monk in the late 1800s. Anyway, he was doing work with peas in his monastery garden, and there were different sorts of peas, and some were green and some were yellow, and some were smooth skinned and some were wrinkled skin. And anyway, he did all these things and kind of discovered the basic genetic laws, and he published in an obscure journal that no one looked at for years and years and years, and then it was rediscovered in the early 1900s, and everyone said, hey, maybe this would apply to what Darwin was doing, because up until that time they still had no good explanation of how evolution worked, of how heredity worked. There were still people right at that time who thought that if you cut off a rat's tail, then the baby rats that it had would miss their tails, and we know that's ridiculous, but this is the sort of thing that was going on. So this is very interesting. I think Triola has a sidebar or two about Mendel's experiments. You could probably find it in the index of the book. This is a tricky question too, so I like it for that reason too. So what happened is we're doing a genetic experiment with peas, and you have to count the peas. And we have a sample of offspring, right? Why is it a sample? Because it's this crop. It's not every pea plant in the world. It's just these peas. And we had 431 green peas and 157 yellow peas. And we want a 90% confidence interval to estimate the percentage of yellow peas. And this sounds like it'll be easy, but there's a little trick to it. Let me show you how to do it wrong, because a lot of students will do this and it'll come up on a quiz or a test and students will do it wrong. So it's important to pay attention to this. Go to stat, go to proportion, go to one sample. We don't have the data, we just have the summary. And here's what students do is they say, we're trying to find the yellow. Okay, yellow is 157. So that's the success is 157. And then what were the green? 431. And the students put 431 here. And this is wrong because that's not the total number, right? This is only the green ones. What's N? What's our sample size? It's the yellow ones plus the green ones. So grab my calculator. Let's put in 431 plus 157 for the green and yellow peas, and I get a total of 588. So the correct number of observations is 588. And this is a very easy mistake to make. So pay attention if they're giving you a total or if they're giving you the rest of the sample. Once we have that, we need to check to see what our confidence level should be. It's 90%. We never change this. This is the only method we use. There are a couple different methods, and we just do the one. We don't even talk about it. There it is. And there's your lower limit, and you have to round to 3 decimal places. So I'm copying 0.237 into the lower limit box and tabbing into the upper limit box. It's 0.297. You realize these aren't as hard as I thought they were. Well, here's the deal. We know, how do we know? Because of the laws of genetics that Gregor Mendel discovered, that the proportion of yellow peas should be 25%. Well, it's not. It's 26.7%. Hey, there's too many yellow peas. Well, that's weird. What did you do? What mistake did you make? I didn't make any mistake. I put these peas in and I did this stuff. Are we bewildered? Have we contradicted our expectations? And the answer is, well, look, we're expecting 25%. We know the true value is between 23 and 29. Yeah, 25's in there. So sure. What's the true proportion? Could be 25. Well, why didn't you get 25? Because I didn't do every pea plant in the world. I only did 588 pea plants. There's a variation among samples, but that's the idea there. We're not surprised by this. So this is a study of older adults, 57 through 85, and almost all of them, look at this, almost 90% are on some prescription medication. So they want to know how many that is. Oh, you didn't tell me how many it is. So again, we have to use our calculator. We know the sample size N is 3362, and we know that 89.5% of them do use a medicine. And so you just multiply those together, right? So 3362 times 89.5%. You'll want to change it to a decimal. So 0.895. And we get 3008.99. We know that can't be right because this is how many people. People is a discrete data value. You can't have 3008.99 people. It's like one guy, he started to swallow the pill and I don't know what that would mean. And luckily they tell us round to the nearest integer. So 3009. Good job. We need now a 90% confidence interval. And why did we have to do this? Well, because StatCrunch is going to ask us for the number of successes. So remember this 3009. We'll go back to our window, we go to Stat, we go to Proportion Stats, we go to One Sample, we go to Summary. How many successes? It was that 3009 that we just calculated. How many observations? There were 3,362 adults. We're doing a confidence interval calculation. We want a 90% this time. Again, I say, why 90? Because they just like to randomly pick it. That drives me nuts. 0.886 to 0.904 after you round it. And look what they do, just to keep things interesting and lively. They say, actually, we want percents. Okay, so multiply this by 100, 88.6%. You just have to move the decimal over 2 places. And the upper limit similarly is 90.4% after I round. Excellent. College students. What do the results tell us about college students? I thought these were old people. I've had non-trads, non-traditional students. I did have a woman in my class who was in her 80s. But in general, I don't think this tells me anything about college students because this is about old people. It doesn't tell me about college students. Well, yeah, it's the same though. No, I'm sure it's not. I'm sure it's not. People are always worried. They're not always worried. They used to be really, really worried. I think less so just because everyone has a cell phone and people think, I don't care if I have brain cancer, I'm still using my cell phone. You can take my iPhone away when you pry it from my cold, dead fingers, right? People are worried, right? Because you're holding up a source of electromagnetic radiation next to your brain and maybe it gives you cancer. And it turns out that they looked at 420,001 cell phone users and they found that 133 of them did develop cancer. Whoa, that's kind of scary. So what's the percentage? The confidence interval estimate, because this is only 420,000 people and there's a lot more who do have cell phones. This might not, I guarantee it's not the true proportion. So let's see if we can find a confidence interval for it. We go to Stat, we go to Proportion, we go to One Sample, we go to With Summary. How many successes? Remember, the word success is arbitrary. It means the things we are counting. No one says, oh, Fred got brain cancer? Great, success. That's sad for Fred, but that's how we count. How many observations? A total of 420,001. I'm not sure how they got that extra one. Does that feel funny to you? I would have stopped after 420,000. And we want a 95% confidence interval. That's already the level they show. I hit compute and I get these values. They're changing it to percents. This is a good thing because these values have a lot of zeros at the beginning. Brain cancer is pretty rare. So I will move the decimal over a couple, and then I'll have 0.026. They want 3 decimal places. 0.026, and this other one is 0.037. What we are saying is that we're 95% certain that the true proportion of people who get brain cancer after using a cell phone is somewhere in this interval. That's what that means. And then they say, well, is this bad? Well, normally this percentage, 0.0216, gets brain cancer, whether they use a cell phone or not. So compare 0.0216 to this interval, 0.216. That's lower. The true proportion of people who develop cancer of the brain after using a cell phone is higher than before people used a cell phone. Is that different? Yeah, it's different. It's not in our confidence interval. Ooh, that could scare me. Let me point out again, all these numbers are made up. If you've clicked similar question, you'd get a different bunch of numbers. Don't change your life because of something you read in one of these problems. Personally, I don't think cell phones cause cancer. And as I say, I'm addicted to mine. I have to use it. I couldn't live without it. This is an interesting problem. I like this problem a lot. And I like it just because it's so scary. Look at all these numbers. Wait, what? What? What they did is they got a bag of candy. I'm thinking M&Ms. Are you thinking M&Ms? I'm thinking M&Ms. And they weighed the candies. And how many grams was a red? There was a red M&M that was 0.889 grams. And there was one that was 0.793 grams. There was one. You think, whoa, this is a lot of. Wait a second, Gary. Aren't we doing proportions in this section? Yeah. Well, these aren't proportions. No. That's why I like this problem. It tricks you. The only thing that matters is how many candies are there? Well, there's 1, 2, 3, 4, 5, 6. There's 38. Yeah, it says that right here. There are 38 candies, and 1, 2, 3, 4, 5 of them are red. And you think, what proportion of candies are red? And I'm thinking 5 out of 38. Yeah, you could use a calculator. Let's use a calculator. 5 divided by 38. It turns out in this bag of candy, our sample bag, 13% or so were red. Well, the company says that 29% of the candies are red. No, they're not. Well, of course they're not. There's normal variation, right? This is just a different bag. Every sample is different. You might get 5, you might get 6, you might get 4, you might get variation. There's nothing wrong with this bag of candy. Move along. Well, wait a second. I'm a statistician. I'm going to do some work here. So what are we going to do? We're going to go to StatCrunch. We're going to stat. We're going to proportion stats. We're going to one sample. We have data, but it's not data of any use to us. The important thing to us is the counts. So choose with summary for this problem. And how many red ones were there? There were 5. And how many candies were there total? There were 38. They want a 95% confidence interval, which is what they've already defaulted to. I hit the compute button and I have a lower limit and an upper limit. They want percents, so I'll move the decimal over a couple and round it to one place. I will say 2.4%. 2.4%. 1, 2, yep. And I'll move this one over a couple. I will get 23.9%. This is quite a range, isn't it? 2.4 to 23.9. There's a big spread there. I told you there was variation in these candies. And then they say, so does that fit? Well, the company says there are 29%. I don't know the true value of P, but I'm pretty confident that it's between 2.4 and 23.9, which means it's not 29. I think I got gypped. I need a different bag of candy. Is the result consistent? No, because that interval does not include 29%. There's not any difference in flavor. Yeah, but I was going to glue them to a cardboard and make a greeting card because, yeah, okay. Well, then it matters. But the red ones and the brown ones and the yellow ones and the green ones, they all taste the same. Here's a problem that students should take interest in because, they're college students, and this is a problem about college students. Triola's making it relevant. Government financial aid for college students. I'll mention, since we've brought up the topic, make sure you're getting financial aid, right? Fill out a FAFSA. I have been on committees. It's one of the things I like to do. I sit on these committees and people submit applications and we give them money. And there are committees that determine, well, there were 12 applicants. We have 6 scholarships. Who should we give them to? And I like to do that. It's one of my volunteer activities as a professor. But let me tell you what really happens, because you're thinking, wait. Yeah, let me tell you what really happens is we have 6 scholarships to hand out, and we don't get 12 applicants. We get 4. That means we leave money on the table. So if you have not talked to your academic success advisor about scholarships, you should do that. I'm not saying you have to take out a loan if you can afford it. I'm not talking about, whatever. But sometimes there's scholarship money that's just lying there waiting for some student to ask for it. So do that. So what do we find? Why are we interested in this? Because we don't want to pay people who are just milking the system, right? We want them to graduate eventually. So what is the percentage of students who graduate on time, as they say, in 4 years or less? We don't know how to do this one yet. The reason is what we're trying to do is we're trying to find out the sample size. I want to get a 3% margin of error, and I want a confidence level of 99%. How many students should I ask? And what am I going to ask? I'm going to say, are you a student? Yeah, they're students. So it's a sample of students. There's going to be 100 or 500 or 1,000 or 20,000. I don't know how many. And I'm going to ask, did you graduate in 4 years or less? And they'll say yes, or they'll say no. And then I'll have a proportion. I'll have a p hat, and I will use it to estimate p. I want my p to be pretty close. I want my margin of error to be 0.03 or less. So let's jump back to the textbook and I will show you the formula for this. Here on page 307 are the instructions to determine sample size. So this is an important question. We mentioned it just briefly in class, the idea being that you want to interview enough subjects or measure enough subjects that you can calculate your margin of error within some specified amount. You don't want to be too far off, but you don't want to do more than that. If you only need to count 100 penguins, don't count 200 penguins. It wastes research money. Use that for something else. And so we would really like to find out what n should be. And there's a formula for it. It doesn't surprise you that it has a critical value, z sub alpha over 2. It has the sample statistics of success and failure. It uses the margin of error. And so, okay, this is great. You plug all this stuff in. Fine. Why are there 2 formulas? So there are 2 formulas because one assumes that you actually know p hat. And why would you know p hat? Well, because I already caught 100 penguins and I found 28% were male. So I happen to know this. This would be, I haven't even flown to South America yet. I don't have my visa. I don't have a ticket or anything. I'm still sitting in Michigan. And I don't know what p hat's going to be. I'm going to go down and find out. What's the difference between these formulas? One says, I actually know it's 28% are male. In that situation, I would multiply 0.28 times the q hat. That's 1 minus 0.28. And that's the value I use here. Here, I have no idea how many are males. I don't know the proportion. And so what would I do? Well, here's the idea. Maybe 50-50, and you say, why do you say 50-50? Because I don't know anything. I don't know anything. So I'm just assuming it's 50-50. Because if I were to say, well, it's 40-60, well, that assumes I know something. But I don't know anything. Well, if it's 50-50, then when I multiply the 50 by the 50, I get 0.25. And that's the idea here. You are usually better if you do know p hat, because anything, this is 50-50 makes this the biggest value you can ever get, 0.25. And you think about it, you say, well, what if it was 40-60? Well, 0.4 times 0.6 is 0.24, which is a little smaller. That your sample size, the number of penguins you need to count, is smaller. That saves you money. If you knew it was 70-30, well, 0.7 times 0.3 is 0.21. We're saving almost 20% of our study dollars, right? Our value of n shrank a lot, going from 0.25 to 0.21. So how can you know p hat? Well, maybe you did this last year, so you might know. Maybe from a pilot study. I need to do probably 1,000 penguins. I need to talk to 2,000 adults about whether they're comfortable in a car. But let's just ask 100 and get a feel for what the percentage is. That's what they call a pilot study. Or someone's expert knowledge. Someone just knows a lot about this. And then you can use this formula. And if you don't know, then you're overestimating. There's a round-off rule, and we don't need to use it. So there's the explanation behind it. The tricky part is that when we say we want to be within some particular margin of error, so our problem that we were just looking at said be within 0.03. What that means is 0.03 on the left and 0.03 on the right. And that matters because of what I'll show you here right now. So we want a 0.03 margin of error with a confidence level of 99%. Assume that we don't know anything about the proportion of students who earn a bachelor's degree in 4 years or less. We go to stat, we go to proportion, we go to one sample. This is different finally. We go to width, sample size. Power is something we will mention very, very briefly later in the course. I might spend 2 minutes on it. It deserves an entire lecture, but we don't have the time, sorry. Width is what we want to know. So use width, sample size. And this is a strange looking thing. It's like, wait, what? But don't worry about the graph. The graph means nothing to you. All that matters here is you have to put these values in. And most of it's copying. There's one tricky part. They told us to use a confidence level of 99%. So I put that in, 0.99. We also have to know the target proportion. This is the p hat. I know nothing about p hat. So what do I assume it is? Well, it's probably 50-50. So that's why this 0.5 is here. Now comes the tricky part. We need to put the width in. And the width, if you look at this, you say it's 0.03. Yep, it's 0.03 on the right, and it's 0.03 on the left, right? Because we have a confidence interval. And our P will be in the middle of a 0.03 up and a 0.03 down. So what's the actual width? It's double this. It's 0.06. So put in 0.06, and they will tell us the sample size. 1844. You notice, by the way, that this changed. Wait, I thought it was 0.06. What happened? What happened is they rounded up. You always have to round up. And you think, that's not the normal rounding rule. Nope. The normal rounding rule depends on 5. 5 you go up and 4 you go down and something. There's a complication to it. Here, we have to have enough. If the answer were 1843.1, well, there isn't a 0.1 penguin. There isn't a 0.1 student. So you have to ask a whole student, and that's why this goes up. So they've already rounded up. What that means is we're actually more accurate than they said. We said, well, I need to be within 0.06. and we're actually within 0.05998. It's not much of a difference. There wasn't much rounding going on here. But anyway, there you go, 1844. And you put that in. The only tricky part, as I say, is you have to double the margin of error to find the width. 1844, great. We'll spend one more minute. Assume that we've done this before, last year, prior studies, 3 years ago. We find that about 55% of full-time students earn bachelor's degrees in 4 years or less. And I'll mention again, remember these numbers are made up. Has nothing to do with you, has nothing to do with reality. But if we happen to know that 55% is the value we found before, then our target proportion is that 55%. 0.55, we have to adjust our width. It's twice the margin of error that we desire. So 2 times 0.03 is 0.06. We hit compute, and hey, we just saved some research dollars. We don't have to talk to 1,844 students. We only have to talk to 1,825. A substantial, I don't think it's substantial. And that's what they ask us. They say, does it help? Yeah, we went from 50% to 55%. It didn't help much. It slightly reduces. Using the additional survey information only slightly reduces. It's nothing to write home about. And that's how you work those.